We'll move to the next talk, given by Yaoqing Huang from Reguang's group, right? Okay, and I think he will talk about the screen light developed in Reguang's group and use it for the gravitational wave detection. Let's welcome Dr. Huang.
Hello, everyone. My name is Yaoqing Huang. I thank Professor Li let me come here to give a report say the screen side application in the gravitational wave and the quantum state tomography. So in gravitational wave, the screen light can improve the detection range. So then we can observe the more remote university image. And then for the quantum state, we demonstrate experimental fast reconstruction Wigner function in phase space for the continuous variable quantum state. So I maybe give a first part talk about the gravitational wave detector. Human first directly the binaural Bell merge in 2050 years. Yeah, in here. So black hole is a rotation and close to each other radiation with gravitational wave signal. The merge process, you can see this picture. Scientists to build a large-scale telescope to measure the gravitational field to produce a weak gravitational wave signal. So the important result is get a 2017 year Nobel Prize. So it's linked the year of gravitational wave astronomy for the many people coming to the data aside for the like the Bell merge of other things. And here is one to show the ground space gravitational telescope. You can find this picture show in America there have two large scale telescope in here. It's called a LIGO. The length is of about have a 4 kilometer length. In Europe, they have a Virgo and a Jewel. However, this Jewel is a mid-schedule length of 300 meter. But and then you can see here have a Kagwa. Kagwa is located in Japan, but they have two advanced feature. The telescope was built in the tunnel underground. It's one tool to reduce the emitted background noise, and using the cryogenic mineral with sulfur material, you want to reduce the thermal noise. However, then in the future, LIGO group want to build a telescope in India in here. I think it want to working in 2025 year. So we can see that there have many telescopes is running and plan to work. For the good news, Kagwa have joined the global acceleration schedule in last April. So now is they have 1, 2, 3, 4, 5 have a 5 large scale telescope to detection the gravitational signal. So I talk about the Kagwa the introduction. Kagwa is built in here in Kamioka in Japan. The length have with 3 kilometer length is a bit smaller than a LIGO scale. The picture is show the Kagwa sensitivity. You can find here to see there are many fundamental noise to limitation final curve shape. So for the ground-based detector, they have a limitation in the low frequency band because of the size scale as well as the low frequency noise such as seismic motion for nice earthquakes of type. So that is why we consider gravitational wave signal in the 100 band, 100 Hertz frequency band in here, because its sensitivity is better than other band. So, however, when we consider in this note, however, the main to limitation the sensitivity contribution from the quantum noise. So, if you can reduce the quantum noise, so you can improve the sensitivity to better. So, in our group in 2018 have joined the Kagwa as a collaboration. My group study focus contribution in to reduce quantum noise with a squeezed light in here. So we have a panel target to get the broadband suspension of the quantum noise like this. So last year, we have demonstrated this idea with a filter cavity to get a frequency-dependent squeezer breaking source for the broadband quantum noise reduction. It's a population in this physical review data you can see here. There is a short main people join these experiments. So later, let us to consider quantum noise how to generate. Actually, the quantum noise is original from the making fluctuation. We can see this simply telescope set up. Making fluctuation will enter the telescope from this detector output port from this kind to the amplitude fluctuation will cause the middle fluctuation and the low frequency and become the radiation pressure noise. You can get this live. And the phase fluctuation of the making fluctuation will become the sharp noise at high frequency. You can see this green curve. So we want to consider these two-term contribution. We can get the quantum noise. You can see the total is like this black curve, like this. So if you can decrease the noise fluctuation in one direction, for example, you can like this. However, according to the Heisenberg principle, if we decrease this direction, the noise fluctuation will increase the orthogonal one. For example, like this. So for this picture is showed we screen in the phase direction. We can align the gravitational wave signal in the phase direction. We can get a better signal to noise ratio like this. In general, in 2019, Ligong and Virgo have demonstrated the channel reduction by the squid phase sequencing line. The results showed this picture as this red curve in here. This black curve is a reference and the long sequencing line. The observability can improve the sensitivity in high frequency range. You can see here. But in low frequency, we can see the sensitivity become worse because of the radiation pressure noise issue. So if, by the way, if we use amplitude sequencing line to inject the telescope, we can find this blue curve. We can find the channel will become the sensitivity become worse. That's this curve. So for the good idea, we need use a frequency dependent screening. In low frequency, we can prepare the amplitude sequencing like this, okay, to reduce the radiation pressure noise. In high frequency, we can use phase sequencing like this to reduce the sound noise. But in medium range, we should prepare a sequencing state in a specific angle like this, so we can get a Bobbitt suspension of the quantum noise. From this theoretical calculation, if we use frequency dependent sequencing, we can reduce the sound noise and the radiation pressure noise at the same time, like this curve. The black curve is without use the frequency dependent. When we inject the frequency dependent into the telescope, the sensitivity curve will from reduce to this blue curve you can see here. Later, I will say to explain how to generate frequency-dependent sequencing. From our experiment, our sequence making source generated from the nonlinear crystal. From here, with the parametric down-conversion process. So we can measure this squid state noise fluctuation by the homodyne detector like this. Because according to the phase metric and the energy conservation, when we pump one photon, will convert to the 2 photon condition. At the same time, these 2 photons, signal and the ion, are correlation photon pair. So we measure the noise fluctuation, we can get this result. About of 200 Hertz, we achieve the screen making step with a screen level of the -4.4 decibel. We correspond to the anti-squeezing level with 50 decibel in here. So we can first prepare the phase squeezing state like this. We also call this frequency independent squeezing like this. So when the frequency independent squeezing is reflected by the filter cavity, the squeezing angle at each frequency is determined by the relative phase, depend on the signal and the ion. You can, I use this diagram to explain. You can see this local beam frequency is mean like this this local beam frequency. The signal and idle is centered to a general, so it's a symmetrical sideband. But when with the filter capacity is working operation in the determined condition like this, the symmetry sideband will express a different phase change depend on the filter cavity dispersion. So you can like this. If you signal, you can see here. Before the input filter cavity, we prepare this type squeezing. But after the filter, you can see the signal is phase the delay only to here. But for the idle light, phase delay to in here. So this direction noise fluctuation will to reduce. But in orthogonal one, the noise fluctuation will increase. So you can from in the quadratic plane, you can see the squeeze state will rotation. So I can totally to calculations for each other the frequency. So we can see when the signal and idle very close to the local beam. So it's a phase delay to about minus 90. So you can see the squeezer state is rotated minus 90 degree. You can get this type is a vertical. So in the median range, you can see the squeeze level is slowly to rotate to the 90 degree. Okay, so actually we can to measure the different coordinating angle such this. For example, from 0 to 0 of 30 to the 90 degree. We can get this noise fluctuation distribution. But however, we can observe after the filter cavity, the squeeze level will decrease because of the optical loss and the sound noise coming in. You can see from this experiment result, in high frequency, we can squeeze with about 3.4 decibel in the phase direction, but in low frequency, we can reduce the noise fluctuation about 2 decibel in the amplitude direction like this. So that. And in general, the experiment is working in Japan in here. So the squeezer and the measuring system are built in the optical bench inside the clean room in here. The red top picture is a filter cavity. The length is about 300 meters. It's very long. And the cavity, the filter cavity mirror is put inside this suspension system. We want to avoid some vibration motion. And then the filter cavity total is built in the making system like this. So give some. So we found here frequency dependent squeezing will enable broadband quantum noise reduction. So you can see when Kagwa detector, if use a frequency dependent squeezer, we can increase about 70% detection range from the blue curve to the red curve in this. So we need to prepare a screen that type, maybe like this. Okay, And then the second part, I talk quantum state tomography. We want to from the measured data, for example, like from the measured data to reconstruct the Wigner function like this. For example, like from the gravitational, from the gravitational frequency dependent screen, let's say we want to convert in the different frequency zone of the frequency Wigner function, like this picture. So give an idea. The picture is show the simply measured system. Homodyne detector in here can measure the wave function of the quantum device here. When we continue scanning the local beam phase, we can get this picture. In our case, we take a 3 megahertz signal from the homodyne detector output voltage and scan the local beam phase here. So we can use reconstruction mesh to convert the experiment data to the Wigner function like this. If we create all population distribution over the 2 pi interval, we can get this Wigner function. So in order to accelerate the reconstruction process, so we built a model with a convolution neural network, and we prepare more squeezing level to train this model to optimize the parameter. Under our testing, we find this model squeeze learner is it can faster than the mechanical who mesh during this construction process. Let's see. So there is a technique have a great potential in the quantum state tomography. So you want to use the data to convert to the Wigner function of its densimetry like this. In the future, we want to this technique could be the monitor the purity of this quantum state toward the real-time quantum tomography. I think this is that's all. Maybe thanks for your attention.
So now it's open for questions. Any questions? No? Maybe I have a question. So I mean for the high frequency detection, right? So what kind of event you are interested in that frequency range?
High frequency because we want this culture fast. I didn't want to waste too many time in here to catch the data.
No, my question is in the gravitational wave detection. Yeah.
I thought in here.
No, first part. Maybe
here.
No, there's one slide you show in the phase squeezing, you have better noise reduction in high frequency range.
Yeah.
Right. I think the gravitational community, they are interested in some event, the binary black hole like that.
Nice.
Oh yeah. Maybe
no.
Next figure. Next. Yeah.
Can find it. How to.
Yeah, maybe this figure. No, there might be some event people want to detect in this frequency range. Few kilohertz.
No, because we build a telescope size. You can imitation with the sensitivity about 100 hertz in this band. But you want to detune this to high
maybe
frequency.
Yeah, maybe I switch to
okay.
Mandarin.
Because the telescope is built in ground base. However, we didn't to build a low frequency because the sound motion like a square, so limited this band sensitivity in low frequency. So in high frequency, in here, if for the telescope length scale, you can, because of the length scale, you use a kilometer. In here, the kilometer is here. So, however, the black hole signal happen, the signal often happen in here range. And also in here range have a better signal to noise ratio in here because the sensitivity is better than other band.
Okay. Any questions? Maybe from online audience? No? So if not the case, then thanks, Dr. Huang again. Yeah, so now we close the session, and this call is today, right? Or you want to speak?
Okay. Yeah. Okay. Yeah. Thank you all. Yeah, for staying here to the end of the first day session. Okay. So tomorrow we will start at 10 a.m. Okay, and with a very brief introduction on the quantum complexity. Okay, and so please join us. By 10 a.m. tomorrow. Okay. See you.